So this is joint work in progress with Emilio Franco from Madrid, Robbie Hansen from London and the Imperial, and Johannes Horn from Frankfurt. And this is actually going to be a, let's say, an update of a talk I gave a while back at Oscar's conference, like more than 3 years ago. And I remember that I finished that talk with 2 questions, or let's say 1 suspicion, 1 conjecture, and a question. The suspicion has been confirmed, so let's confirm. But the question, the other second question, which was dependent on the suspicion, remains. And so I will end up with that question and some extra comments. But actually, I can show you the question right now. The question is this. So not very informative, but let's go on. Okay. So, okay, let's start with these first few slides are like, I'm going to introduce notation and talk about these objects that most of you know very well, but I need to introduce the notation and probably it's helpful to students and so on. Okay, so Higgs bundles, we all know this. So X will be a curve, genus at least 2, K the canonical. Here are the Higgs bundles I'm going to consider. So the Higgs field, no conditions on the Higgs field, of course, holomorphic and so on. The vector bundle also no conditions. So this means that I'm considering Higgs bundles for GLNC. For technical reasons, let's say for simplicity, I'm going to take Higgs bundles for this degree. It's not very important. And here's the moduli space of semi-stable Higgs bundles, this curly M, introduced by Nigel Hitchin in the 80s and Simpson also in the 90s. So this is a quasi-projective variety of this dimension. And as already been said various times, it comes with a complex holomorphic symplectic form on the smooth locus of M, okay? So for this degree, M is not smooth, but I'm going to quickly go into the smooth locus. So whenever, I'm not going to distinguish the notation, so I'll be in the smooth locus basically all the time, okay? All right, so also this has been introduced by various people here, including Nigel in his lectures. So this is the famous Hitchin map, which out of a Higgs bundle, a semi-stable Higgs bundle, gives you like the coefficients of the characteristic polynomial of phi. And that takes values in this vector space of sections of powers of k, of the canonical. And I will denote that by B. This is also called the Hitchin base. And the important thing is that out of an element here, out of an element in this space, we can cook up a so-called spectral curve, which lives inside the total space of K. This is my notation for total space. And this is actually, so it's not important, the equation itself for this talk. Of course, it's important in general, but so here's the equation. So it's the spectral curve is the zero scheme of this section of the pullback of Kn into the total space of K. So out of this, for instance, you can see that all spectral curves are linearly equivalent as divisors in this total space, okay? And so this pi will be the projection. This lambda here, which appears here, is this tautological section. When you pull back a bundle to its total space, you always get a tautological section. And this is the restriction of this projection to this curve. And this is always a finite ramified N cover, okay? So for a generic element in the base here, this curve is smooth, okay? And I will denote by this symbol the Jacobian, oh, I should have said there degree 0, so the Jacobian of CA, okay? So if CA is smooth, this is the Jacobian we all know, but I'm putting there generalized Jacobian because most of the times this symbol will be attached to a non-smooth curve. So in that case, This is non-projective, it's not compact. It parameterizes degree zero line bundles on the curve. And if the curve is not smooth, then we have to compactify it. There are various ways, and one of the ways, which is the one I'm using here, is compactified by allowing rank 1 torsion-free sheaves on that curve. Okay, this is a compactified Jacobian, and it's a projective variety, singular now, and this is going to be our object. Okay. Okay. So now this other famous theorem, which describes the fiber of this Hitchin morphism. So you pick any point in the base, and the fiber is this compactified Jacobian of the spectral curve. Okay, and the isomorphism is you pick a rank 1 torsion-free sheaf, or most of the time it's going to be a line bundle, and you push it forward under this projection, and you get a vector bundle, and the Higgs field is induced by pushing forward this tautological section, like multiplying by this tautological section. Okay? Okay. So what this says is that out of a Higgs bundle in a fiber, I have this data, which is a curve, the spectral curve, and the sheaf corresponding to this Higgs bundle, and we call that the spectral data of a Higgs bundle. Okay? And so the thing is that we can think of Higgs bundles, there's one-to-one correspondence, as rank 1 torsion-free sheaves supported on some spectral curve inside the total space. So this is another way of thinking of Higgs bundles, okay? There's this semi-stability condition, and here also, here I'm not going to talk about this semi-stability condition because I'm going to look at very special singular curves, which are nodal, so integral, irreducible, and reduced. And in that case, any rank 1 torsion-free sheaf in those curves is automatically stable. And so the Higgs bundles on this side will also be stable. Okay? So that's why I will always be in the smooth focus of the Higgs bundle moduli space. Okay, so this is important. So this is two ways of thinking of Higgs bundles. Okay, so this is the usual picture that appears many times. So Joy already showed the picture. So as I already said, for A generic, the fibers are the Jacobians, so 1 billion varieties. And so this gives us the famous integral system, which is called the Hitchin system for everybody except Nigel. Okay, so this is the picture. So, and here you see the fibers, Jacobians, okay? But then they degenerate into some singular fibers because the compactified Jacobian are singular. And I'm going to be interested in these locus, okay? All right, so now let's slow down a bit. So we'll focus on irreducible nodal spectral curves. So again, irreducible and reduced. Okay? And inside this Hitchin base, I'm going to denote by B1 the locus of points in the Hitchin base whose corresponding spectral curve is nodal, irreducible, and with exactly one node. Okay? So this is a codimension 1 subvariety of B. No, well, not like it's open in B, okay? But it's a codimension 1 subspace. So take one such A there. So our curve CA, our spectral curve, is now nodal. And so I can desingularize it, take the normalization. And so I will always denote sigma A, the normalization of the nodal curve. So sigma A is now a smooth projective curve. Okay? And this new A is the normalization map. So this normalization map induces a obvious map between the corresponding Jacobians. And here I note that this is the generalized Jacobian. So by pullback, you take a line bundle on CA, pull it back, the degree remains the same. And I have this C star kernel of this map which is basically the gluing data, okay? So by the way, I took that weird degree of Higgs bundles at the beginning exactly in order to take really Jacobians of degree 0 things here, okay? All right, so this is why this Jacobian, this non-compact thing is also called a semi-abelian variety, it's just a name. And one important thing is that this map, so this is dense inside it, it's compactified Jacobian because the curve is irreducible. But this map does not extend to the compactification, okay? And this is important, and this is actually a reason why I will have to introduce an extra object to below, okay? All right, so because, I mean, this is the connection, like the relation we have between the Jacobian of this singular curve and the Jacobian of the smooth curve. But since this does not extend to the compactification, we lose the relation, only out of this data, we lose the relation between the compactified Jacobian and the Jacobian of the normalization, and that's why I will have to introduce these other objects. Okay, so let's now in just words give you the idea of I'm already saying that they are Lagrangians, but okay, but the Lagrangians that we built. So take any A in this locus for nodal spectral curves, and take those Higgs bundles, remember the Higgs bundles, and you can think of them in terms of spectral data, Higgs bundles whose corresponding spectral data lies in the closure of a fiber of this pullback map here. So fix a point here, take a fiber, it's a C star, the fiber is in this Jacobian, and now take the closure of that fiber, it's going to be here, okay? And so that's going to be the spectral data of the Higgs bundles in this space, okay? But now, okay, I'm taking the closure here, but we want Lagrangians to be closed. So what I need to know, because B1 is not closed, what I do, an extra step, is that I take the closure of this. So the thing is that I allow A to be going to the closure of B1 inside B. So okay, probably allowing worse singularities. Okay, so now let's go more into this and to explain better. So take, again, another A in this B1. So we have this picture, the normalization. This is the projection of the spectral curve. And so I take a corresponding projection of the normalization into the base curve by just taking the composition. And just for the purpose of simplicity for this talk, take this point in this Jacobian corresponding to the trivial line bundle on the normalization. So we have this map again that I told you about, and here's the definition. So I'm taking I'm putting in symbols what I said in words. I'm taking the fiber here and taking the closure. And this is going to be a P1. And this lives inside. So I'm taking the closure inside the compactified Jacobian. This gives me a P1 inside the compactified Jacobian. Okay? And so this is something living inside a fiber of the Hitchin map. Okay? For now, this only defines something inside a fiber. Okay? So a generic element here, of course, is a line bundle on the spectral curve whose pullback is this trivial line bundle. And by generic here, I mean something in C star and not in P1. Okay, now what I have to do is to vary A, right? And here is like a rough definition. Just what I do is that I have this over each fiber, and what I do is that we take the subvariety obtained by taking these LAs and vary along B1, okay? And then by taking the closure. So here I'm being quite sloppy. This can be done in a rigorous way. So what one has to do is take a family of nodal curves over this B1. That gives me a family of normalizations. And then I take the corresponding relative Jacobians of the families, and I take a section of the relative Jacobian of normalizations. So this is one example. So for instance, if for each normalization you take the corresponding zero, the trivial line bundle, then you have a section of these Jacobians of these normalizations, of this relative Jacobian, okay? So I mean, but the idea is just this, but this can be done in rigorous terms. B1 is open, yeah, because you can, like you take a nodal curve, you can deform it to a, like, for instance, you can deform it to a curve with one more node, or you can, right? Exactly one node, but I guess. Yeah, right. But you can deform it. What I mean is that I have things in the boundary which are not in B1, right? You can deform a spectral curve into something that's. Yes. Yeah, okay. Right, so this may not be clear here. In order to see that this is exactly a P1, I would have to introduce, remember that I told that I will have to introduce another object. And actually to see this, I will, these P1s comes from this another object that I will introduce in a few slides, but I'm trying to delay that in order to keep things more readable for now, okay? But out of that, it will be clear that it's a P1, okay? All right, so okay, so now we know that this subvariety maps into this closure of B1, and on B1, if you restrict to B1, it's a P1 bundle, okay? Because of these P1s. Okay, so everything here is for one node, but actually this works for any number of nodes. Actually, the number of nodes is bounded. This is because of the degree of ramification of the spectral curves into the base curve is bounded. It's actually bounded by this. And for higher nodes, what you get is instead of P1s, you get P1 to the K, okay? But actually, this also makes sense in the degenerate case, or let's say, for K equals 0. If you do this for K equals 0, then everything degenerates, and like sigma A equals CA, and what you get is precisely the Hitchin section, okay? So this is kind of generalizing in some way the Hitchin section for these closed subvarieties of the base. All right, so yeah, actually, let me just to maybe. So you have your base, the Hitchin base, and here, okay, you have the Hitchin section, right? Oops, not this, right? Something isomorphic to the base, but here inside you have these B1s, and now here what I'm doing is that over these B1s I'm putting P1s, and you can degenerate things in B1, right? To things with two nodes, and here what I would put here is like a P1 cross P1, okay? So the fibers increase dimension when you go to smaller dimension loci in the base. Someone, sorry?
Yeah, so
if yeah.
In some sense, the fiber is isomorphic. So the fiber is isomorphic to compacted by Jacobian, but
in this case,
it's not like an equality, right? It's an isomorphism.
I mean, yeah.
Pressurized by-
Okay, so for the degree that I took at the beginning, this weird degree, the fiber here is exactly. That's why I took that, just a simplification. Otherwise, we would have to do that. All right. Okay, so here's the first theorem, is that this L is Lagrangian, okay? And you see there, like, the dimensions match what we'll see here. So this L is a Lagrangian. So, and here's, let's see this. I mean, the proof is like, here is a sketch of the proof. I'm going to be quick here. So take a generic point in this L, and by generic, I mean that it's something on some A on really a nodal curve, and something which comes from a line bundle, not a torsion-free sheaf, not, yeah. And so here's the tangent space to the moduli space at this point. And we have the derivative of the Hitchin map. Since we're taking P to be coming from a line bundle, the derivative is surjective. And so this is a tangent space at the base, right? And you can write the tangent space at the base as this H0. And here is the tangent space to the fiber, tangent space to the Jacobian, okay? And you can also write it like that. So we're interested in our L. So what is the tangent space to the fiber? Remember, the fiber was P1, so we're in C star. Here's the tangent space, it's a C. And here's the tangent, so it maps onto the tangent space to this B1 loci. So what the Hitchin base parameterizes are these deformations of spectral curves. What this B1, the tangent space to B1 parameterizes is equisingular deformations. You want to deform, but you want the deformed curves to still be nodal. So these equisingular deformations were studied by Italian school. They are well known. And if you, I mean, here there's some work on identifying these equisingular deformations with this subspace of the Hitchin base, of the tangent to the Hitchin base. It turns out that these inclusions are actually inclusions coming from exact sequence. So this is the normalization, the exact sequence on the nodal curve, which by pushing forward, give this exact sequence on the base curve. And by taking cohomology, you take this, you have this exact sequence in cohomology. And if you note, so here the symplectic form on the moduli space, it's like basically pairs these directions with these directions. This is basically Sech duality. So the directions here, if you look, this is dual to that. So these directions here, the directions here which map to ones here, pair with those. Okay, so which means that the directions there will not pair with those. So that's isotropic. Okay, and now the fact that it's dimension, half of the dimension is easy because the base is half dimension. This is one less the dimension of the base, but that one less is there. Okay, so it's Lagrangian. Okay, very easy. Okay, and why do they call them Lagrangians of Hecke cycles? Because, so let's now denote our node of our spectral curve by P. Let X be you project the node into the base curve. So it turns out that if you have this Higgs bundle in our Lagrangian in a fiber H, then remember that the Higgs bundle is the push forward of a sheaf on the spectral curve, and the Higgs field is this one. Then it turns out that this sheaf actually fits in this exact sequence. It's you push forward the trivial sheaf on the normal curve, and you project onto the nodes. This is in CA, and you take the kernel. Again, this is not clear. This will be clear. This is more clear with these other parabolic modules that I'll talk about. But in any way, F will fit in this sequence, and CA, you project onto X. So here you push forward onto X. Here you'll get E, and you get, so what this says is that the bundle is a Hecke modification of this other vector bundle on X. It's a Hecke modification at the point little x. And with some extra work, one can see that actually this is a Hecke modification, not of just bundles, but of Higgs bundles. the Higgs fields go along. And so the Higgs bundle is actually a Hecke modification of this Higgs bundle. You can think of this as a Higgs bundle, naturally. So that's why I call them Lagrangians of Hecke cycles. And these Hecke cycles, the things parameterizing, are exactly the P1s. Okay, so far, any other questions? Okay, so let's go now to second part, branes and mirror symmetry. I'm glad that Miguel gave the talk before me because he gave a much better overview about this. I'm going to be very, very vague here. So having a Lagrangian, when I have a Lagrangian on M, I automatically think as a brane in M, okay? So M is this non-compact Calabi-Yau, and it's hyperkähler. This has been coming up various times. And here we have these generic dual tori fibrations, the ones that Miguel was saying for dual groups. But remember, we are in GLN. GLN is self-dual. So actually here is the same fibration, but the fibers are dual, right? And whenever we have this, SYZ mirror symmetry says that mirror symmetry should apply to this, to the moduli space. And when mirror symmetry applies, we have these special objects called branes, but this is hyperkähler, so we have these even more special objects, which are the BBB and BAA branes. So what's a BAA brane? And only for supports for now. So a BBB brane is a hyperholomorphic subvariety. So holomorphic with respect to I, J, and K, these three complex structures. And the BAA brane is a complex Lagrangian subvariety with respect to my symplectic form, okay? And this symplectic form, this is the real symplectic form for complex structure J. This is one for K. So this A's here means that this thing is Lagrangian for J and K, and then, of course, it's then Lagrangian for the complex symplectic form. Okay, so this is only for supports. But now branes have more structure on them. They have sheaves or bundles. So a BBB brane is actually a hyperholomorphic subvariety, but together with a hyperholomorphic bundle on it. So a bundle with a connection whose curvature is type 1,1 in 3 complex structures. So this is I think it's a well-established notion. For BAA branes, the story is a little different, I think. So BAA branes have been considered as Lagrangians with a flat bundle. So they've been defined like that. But actually, that flatness condition seems to be oversimplified. And it's not me who says that. It's Gaiotto and Witten, so we better take it into account. So they say this in this paper, and there are other, people from physics who say, so the Gaiotto and Witten say that a rank 1 A brane, okay, L, so a Lagrangian with a bundle is usually described as a complex line bundle with a flat unitary connection. Then they say that this is in general oversimplified, and they explain it's due to some I forgot the name, the word they say, some corrections or some anomaly. That's it, some anomaly, and then they refer to a different paper, but coming from physics, so I don't understand that. And so but then they say the correct global statement is that L is a flat spin C structure over the Lagrangian. Okay? So for us today, a BAA brane, we're going to follow their advice, is going to be a Lagrangian with a flat spin C structure. So what is this? So spin C is spin M, so the double cover of SOM, times U1 modulo this Z2 acting diagonally. And so every complex manifold admits a spin C structure, so a lift of the SOM structure of the tangent bundle to spin C, but they don't want just spin C, they want flat spin C. So an oriented Riemannian manifold admits a flat spin C structure if its second Stiefel-Whitney class is the reduction of a torsion class in H2MZ. So in other words, this means that this W2M is the first chain class of a flat line bundle. Okay, this is the obstruction. Now, what's important here and what we're actually going to use is if you have a spin structure, then you automatically have a spin C structure. But you're having a spin structure, the obstruction is that this one is 0, right? And then you just take L to be the trivial line bundle, okay? So the important is that if your manifold admits a spin structure, then it admits a flat spin C structure, and will be in that case. Okay. I'm sorry? Well, this is higher dimension, right? So yeah. Flat means that this one is torsion. Yeah. Oh, this little m is like the dimension. Here it would be the dimension of m. So, or maybe, yeah. Well, just like SOM or. So we have this conjecture. I don't know if I should call it a conjecture. I mean, this claim by Capucin and Witten that they say that mirror symmetries should exchange BBB and BAA branes in M. Again, I'm going to be not going to these morphism things. And so mathematically, this should be realized by a Fourier-Mukai transform along the fibers of H. And dual branes, we'll call dual branes in M, so branes which are exchanged under mirror symmetry. And what is known is that the supports of dual branes have the same image under the Hitchin map. Okay? Precisely because it's a Fourier-Mukai along the fibers. Okay? So one way to test this is to restrict to a generic fiber and see what happens there. Do the Fourier-Mukai on an intersection of a generic fiber. But remember that our Lagrangians do not go to the most generic fibers, which are smooth fibers. The most generic that we can be in our case is nodal curves. Okay, so in our case, the restriction is going to be on fibers corresponding to nodal spectral curves. Okay, so here's what we want to do. So remember the definition of our Lagrangian, take a point in the base. So our Lagrangian intersected with the fiber, so this is nodal spectral curve, is the closure of the inverse of the pullback map. And I was fixing this trivial line bundle, okay? This is P1. So the intersection of our Lagrangian with a fiber is P1. And I'm going to test mirror symmetry here. And according to Gayotto and Witten, I should not put there a flat bundle, but I should consider it with a spin structure. So on P1, spin structure is O-1, because the canonical is, spin structure is the same, choosing a spin structure is choosing a square root of the canonical, which is O-2, so there's O-1. So I'm going to, because spin is flat spin, as I told you. So I'm going to consider this intersection equipped with this line bundle. So the goal to test mirror symmetry is to compute the Fourier-Mukai transform of this line bundle thought of as a sheaf or a complex, but supported only in 1 degree, in the derived category of the compactified Jacobian. Okay? This is a sheaf here, so a complex. Not full supported, but only supported in there. Okay, this is the goal, to test mirror symmetry. Okay, all right. So I'm going to go to this now. Any questions? All right. Yes. Okay, I think this will become clear, but so one way to, well, let's see, if you have, well, how do you obtain a line bundle on the nodal curve out of a line bundle on the normalization? You take a normalization? I am, yeah. I mean, this is not me who I mean, that these P1s arise, this is known for a while in like, yeah, exactly. That's what I'm going to talk about now. Okay, maybe we can discuss that. Okay. All right, so let's go now to Fourier-Mukai transforms and normalizations. So here's again the same picture. Now I'm going to remove the A. This is all in some spectral curve to not. So on our normalization, this is a smooth curve. We have the Poincaré line bundle on the Jacobian. This is a universal family of line bundles over the Jacobian. And here we have the Fourier-Mukai transform of the derived category of this abelian variety. You just have take a complex here, pull it back to the product, tensor with the Poincaré bundle, and then push it down to the other projection. Mukai proved that this is an equivalence of categories, and this is a Fourier-Mukai transform. Okay, this is the classical Fourier-Mukai transform. We don't want to do this in this case. We want to do this in this compactified Jacobian, and this Fourier-Mukai transforms the generalization of this to the compactified Jacobian was handled by Dima Arinkin, where he constructed this Poincaré sheaf on the product of the compactified Jacobians. It's again a universal family for rank 1 torsion-free sheaves. And he defined the corresponding Fourier-Mukai transform associated to this Poincaré sheaf, same formula. And he proved that it's again an equivalence of categories. And so our goal is to perform this to this O-1 as a sheaf, as a complex there. So in order to do this, we have to compare these two Fourier-Mukais. That's our strategy, because this is well known. And in order to do this is this other object that I'm going to introduce now, which is these generalized parabolic bundles, but also known as parabolic modules, okay? So what are these? So take a node, your node on C, P. So normalize it. You get two different points on the curve, on the smooth curve. And what's a parabolic module for this normalization is simply a pair, okay? MV, where M is a degree 0 line bundle on the smooth curve, and V is a one-dimensional subspace of the fibers of M over the 2 points over the node, okay? Whoa. Okay, so there is a moduli space for these objects. So Husha-Bosle introduced them exactly in this case, in this nodal case, and she called them generalized parabolic bundles. But then Cook, former student of Peter Newstead, generalized this construction for wide generality, for other singularities, and so on. So this is a smooth projective variety of dimension in the genus of the curve. Of course, this V, what this V does is records the gluing data to produce a rank 1 torsion-free sheaf on C, okay? All right, so here's the map. More precisely, we have a map from these parabolic modules to the compactified Jacobian, which out of a parabolic module, you just take the kernel of this projection, okay? So this means that this is going to be a rank 1 torsion-free sheaf, which is in the kernel of this projection. So, which means that inside this sheaf, at the point P, coincides with this vector space that we're choosing to glue things. Then we have another map to the Jacobian of sigma, which is just a forgetful map. To MV, take M, the line bundle. Okay, so now what Usha-Bosler proved in this case, and then Cook proved similar things in other singularities, is that this map here is always finite, and it's a resolution of singularities of the compactified Jacobian. So in particular, this parabolic modulus is also a compactification of the Jacobian of C, a different one. And this morphism here, this forgetful map, is a P1 bundle because the fiber is V. It's just a choice of a vector space. So here's the picture. You have here a finite map whose restriction, when you restrict to the Jacobian, is an isomorphism. So this is a compactification of the Jacobian. And here you have a P1 bundle. Okay? So recall that our map, our pullback map did not extend to the Jacobian, to the compactified Jacobian. But now it extends not to the compactified Jacobian, but it extends to this other compactification, this parabolic modulus moduli space, via this resolution. Okay? So this new dot here, it's a P1 bundle, is a fiber-wise compactification of this pullback map. Moreover, if you restrict this map here, this singularization, if you restrict it onto a fiber of nu dot, this gives you an isomorphism onto its image. That's what I was saying. Okay. Okay then. And so that's how we see the intersection of our Lagrangians with the fiber as a P1. Okay, so this could be another way to define our Lagrangian. Okay, so in particular, we have here O minus 1 appearing here from this P1, okay? All right, so here's so another thing is that this parabolic moduli space is a fine moduli space, also proved by Usha-Bosler. And what's this universal object is that here I have the pullback of the universal line bundle on sigma times Jacobian of sigma, normalized at some point. And I have this curly V, which is just the tautological line subbundle of this restriction of the pullback of the universal bundle to P plus and P minus, so the point above the node. Okay, so this is kind of a tautological bundle because the fiber over this parabolic module of this curly V is exactly the subspace I'm taking, the one-dimensional subspace I'm taking of this MP plus and MP minus. Okay. So this is the universal object. And so remember that the fiber of this new dot of this projection onto the Jacobian of sigma is a P1. And so just by definition, the restriction of this bundle over P mod, if you restrict it to a fiber, then you get O minus 1. Okay, so this is just to recall what we had so far, because now I'm going to state the theorem. Again, nodal curve, the two Fourier-Mukai transforms, this normalization map, the singularization of the compactified Jacobian, this P1 bundle, and this relative tautological bundle. All right, so, there's two extra pieces of data that we still need. This is basic. So I will have the Jacobian of degree -1 line bundles on my smooth curve. Of course, this is isomorphic to the Jacobian of degree 0, just by tensoring by O of y0, a point here. This is usual translation. And I also have this embedding. This is important. So if I have the Jacobian of degree -1, so if I have a line bundle of degree -1 on my normalization, and if I push it forward to the nodal curve, I get a rank 1 torsion-free sheaf of degree 0, the degree increases, but it's not going to be never a line bundle. It's going to be really something in the singular part of the compactified Jacobian, okay? So this gives you an embedding of this Jacobian of degree -1 line bundles on sigma into the compactified Jacobian. And so the image is going to be the singular part of the compactified Jacobian, and this is going to be important now. So here's the theorem, the one we didn't have when I spoke at Oscar's conference. So take any sheaf on this Jacobian of degree -1 line bundles on the smooth curve. So we have the following isomorphisms on the derived category of the compactified Jacobian. So the Fourier-Mukai transforms of the push forward of this sheaf. So this is something sheaf or complex. This is something here in this here. And I have here the formulas for the Fourier-Mukai transforms and its inverse. So what you do, you have to, first you take your sheaf into Jacobian of degree 0 by this translation. You perform the usual Fourier-Mukai. That gives you a sheaf on the Jacobian of degree 0. You pull it back by this bundle. Here gives a sheaf on parabolic modules, tensor by this tautological, relative tautological bundle, and then push down by this normalization. At least you see that you end up in something on the same space. And the inverse one is similar. Here we have to like tensor by the canonical line bundle of the parabolic modules, moduli space. Okay, so this is the same theorem. And what we're going to do is, so we will apply this inverse Fourier-Mukai by taking the trivial sheaf on the Jacobian of degree -1 of sigma, okay? So what do we do? So first here we have to take the push forward onto the Jacobian of degree 0, but this is trivial, so it's going to be trivial there. And the Fourier-Mukai transform of the trivial line bundle over the Jacobian is a torsion sheaf supported where? Supported at the point corresponding to the trivial bundle over the curve. So supported at 0 over the Jacobian. This is how classical Fourier-Mukai transform works, okay? So this is, I'm transforming a line bundle over the Jacobian that gives me a sheaf supported only at this point. So now let's then apply this formula to this guy, okay? So then from this line, we just saw that here we have a structure sheaf of this point. So, but pulling it back is basically restricting this to the fiber of this map, okay? But what is the fiber of this map is P1, okay? P1, and remember that V over P1 was O minus 1, so I get there O1. And one thing that I didn't say, but it's true, is that the canonical bundle of the parabolic modules restricted to a fiber goes to the canonical bundle, so it's O minus 1. So I get really O minus 1. So I said it's O minus 2, so now what I get is really O minus 1. So I have this. So now I apply the usual Fourier-Mukai, it cancels, and what I see is that the Fourier-Mukai transform of this sheaf as a sheaf there, it's the trivial sheaf over the image of this embedding, right? Because this is, okay? So in other words, what we're saying is that the Fourier-Mukai transform of this, or in words, what we just saw is that the Fourier-Mukai transform of this sheaf supported in our Lagrangian over a fiber is the trivial sheaf as also a sheaf inside the fiber. Okay, and it's the trivial line bundle over this image. Okay, so this image has been considered by Nigel a few years ago, where it's actually, in this case, this C. So Nigel introduced this loci, which I'm now calling C, is the closure of the loci where the rank of the map, of the Hitchin map, drops by 1, okay? Actually, it can drop more, but I'm considering dropping just by 1. And in his words, this is called the first critical loci of the Hitchin map. So Nigel also proved that the spectral data of elements here is exactly the image given by the image of the Jacobian of the normalized curve of degree -1 inside the compactified Jacobian. So it's exactly this image here. Okay, for some A in B1, or also still nodal curves. Actually, this C is a subintegral system that Nigel also mentioned in his talk. Okay, so theorem C, this theorem here can be restated as that fiber-wise mirror symmetry exchanges the line bundles here over the intersection of our Lagrangian with the fiber, with the trivial bundle on this intersection of this critical loci with the same fiber. Okay. So in particular, this also holds for the supports. Okay, so the supports of our Lagrangian go to the support of this critical loci. So just to recap, our Lagrangian it's a Lagrangian with a flat spin C structure. Fourier-Mukai exchanges this line bundle with the trivial line bundle here. And according to Kapustin and Witten, BAA branes should go to BBB branes. However, Nigel showed that C is not hyperholomorphic, okay? Is not hyperholomorphic. So it cannot support a BBB brane, okay? So so that's the question I had. Now you understand the question I had at the beginning. And so just some comments, I'm almost finishing. Maybe the correspondence, I mean, this mirror symmetry has been tested many times, but on the smooth locus of the Hitchin map, so smooth spectral curves. Maybe some corrections, and I don't know what I mean by corrections, but may need to be taken into account when singular curves appear. Maybe this is some kind of asymptotic mirror symmetry. And one reason to think about that, or to suspect that, is that so Johannes Horn, and Lee proved recently that, okay, so this C is not hyperkähler, but there is a semi-flat hyperkähler metric on this subintegral system C, remember, which, so at the limit when you go to, at infinity, when you go to infinity on the Hitchin base, which approximates exponentially the restriction of the hyperkähler metric on M to C. This restriction is not hyperkähler, as Nigel proved, okay? But it can be approximated by a hyperkähler metric. I mean, in other words, this is basically saying is that C is not hyperkähler on the Higgs bundle moduli space, but when you go to infinity on the base, then it becomes hyperkähler. And our Lagrangians, when you go to infinity, are still Lagrangians. So maybe this is like a shadow of some mirror symmetry at infinity. Just to finish, so everything can be adapted for any other number of nodes. But remember that the number of nodes was limited above, so there is a maximal number of nodes. And this maximal case has been studied before, actually, by me, Emile Franco, Peter Gotten, and Anna Pion. And there we showed that the supports, now this is not the same Lagrangian, and this is not the same critical loci, it's the case version of those. But for maximal K, the supports are still exchanged under mirror symmetry, but in this case, C is hyperholomorphic in this maximal case of nodes. So yeah, So then I stop here.
Questions?
So is there a reason why you have to fix that particular degree? Would this work on Higgs bundles of different?
One at the beginning,
Yeah, like
just to keep this talk more simple. There's no reason.
so it works for any degrees?
Yes. Yes.
When you have more than one node, what is the bundle over the?
When I have?
When you have when k is bigger than 1.
Oh, it's P1 to the K.
Do you have a line bundle over this, or do you have a higher rank bundle over this?
Oh, instead of O1 of O minus 1. No, it's the so it's like you take O minus 1 on P1, and then you have all the projections of P1 to the K to all these factors, and you pull them up to the product and twist. It's like this external tensor product. It's a line bundle still.
Still a line bundle?
Yeah,
okay.
It's a line bundle.
Yeah, and there's a flat line bundle, is it? I mean, are we looking at a?
No,
it's not. Well, in the semi-flat approximation, does it have non-trivial curvature?
Oh, you mean in their results when you go to infinity?
Yeah.
That I don't know. Yeah, that I don't know.
Okay.
Other questions? I had a question. So is there an explicit example where one can, see everything in action? Like a very simple but explicit example
Of
your, computations?
Yes, we give, I can't give you now, but we have a baby case, which is, I think we have a baby case for this Fourier-Mukai thing in a case where we get an elliptic curve with one node. Yeah, that case doesn't arise in the Hitchin system. But it's like a case, and we see it very clearly appearing this. And that's actually a case that we know for a long time, and that kept us, because we were obtaining different things and that were not matching with that case. And so, yeah, elliptic curve with one node, and then I can show you.
What is it about having more than one node that makes it hyperholomorphic?
It's, I don't think it's, I would guess, so Nigel proved that for one node, this is not hyperholomorphic. I would guess that for 2 nodes, 3, etc., it's still not hyperholomorphic. It becomes hyperholomorphic when it, at the limit, yeah. At maximal. And one way to see that is that in those cases, you can think of this C. Actually, Nigel also proved that for maximal nodes, this is a hyperholomorphic. That this C, you can think of this C as in a different way. It's like a fixed point. So take a Higgs bundle and tensor by a line bundle of order n. That has fixed points. And this C for this maximal number of nodes is the fixed points of variety. And it means, and then this, out of this, you can see that you can describe this C in a very special way, and then you can see immediately that it becomes hyperholomorphic. So in other words, it's like Higgs bundles which come from an unramified cover, as push forwards from an unramified cover of my base curve.
Any further questions? If not, let's thank André again.